Hey Daniel, I hope you're all right. This is Martin. We spoke on the phone a while ago. Um, I was working on my dissertation back then. Right now, I've written all of my dissertation, handed it in, and about a week and a half ago, I started working on this little project. So I've used Django and the FHIR API and the drchrono API and some cool artificial intelligence to build this project. And yeah, right now I'm just going to show it to you. You can check it out online at martinborg.com. Um, all of it should work right now. So the actual project is just in FluMap over here. And what I did is I built a flu epicenter detection app. So basically, when people get the flu, they tend to have the flu in clusters. So when you're in such a cluster, obviously there's a higher chance of you contracting the flu than when you don't live in one of those clusters. So I'm trying to find those clusters from a data set of patients that either have the flu or do not have the flu. And I've implemented a way to load patient data from the drchrono API. I also made a way to automatically generate patient data since I don't have that many patients in my drchrono account, and just helps to actually show what I'm doing. And then patients can log in to using the FHIR API to check whether their address is actually close to one of the detected flu epicenters. So practical uses of this would be determining how to allocate resources when there's flu outbreaks. Not just the flu, but for example, a while ago you had the Mexican swine flu, and obviously it would have been really useful if the government would have been able to find where the infections are coming from and where where resources are needed. Also, can be used to predict where future flu outbreaks might be, or when those clusters move, you can try to do some analysis and try to predict where they will move to next, and then patients can or doctors can let their patients know, or maybe administer some flu shots strategically. So yeah, let's get started. First function I want to show you is just loading the patients using the drchrono API. Um, and I think I just forgot to clear my cookies, so now you don't actually see me log in. Um, but yeah, you'll have to believe me on that one. You can do it yourself to check it out. I only have two patients who actually live on this map in San Jose, which is one of the patients that I received when I created my account, and this patient that I created. This patient lives at the drchrono headquarters. So I'm hoping my address to latitude longitude mapper um, library that I used works well enough for you to believe that this is about where the drchrono headquarters is. Um, and he has the flu. Um, So a call to the drchrono API is made to check whether each patient has the flu. And if they have the flu, then they're displayed using a red dot. And if they do not, they're displayed using a blue dot, like here. Um, and yeah, let's just dive into my code so I can show you what's actually happening there. So this just calls the load function in experiment.py, which is in FluMap, in the FluMap app. And yeah, it uses the social auth backend from drchrono that is in the birthday wisher API that I found on GitHub, with maybe some minor adjustments, but not a lot of them. So I'm just loading all patients using one of the API functions I wrote. Then using geolocator to find the location for patients that I haven't that aren't in the database yet, and then it determines whether they have the flu using the call to the API, and it determines the latitude and longitudes. It determines whether it's on the map whether they're on the map that we're using, and then it saves all that info. And then if the patient is already loaded into the database, just a check is made to see whether their flu Boolean has changed, since that's the only information that would change often, I think. Um, and then all the patients are saved in a different database using just their X and Y component and whether or not they have the flu. Um, and then displayed on the map using the map manipulation file that I've built, which basically just uses a NumPy array to represent the image. And then you take all of the patients and their coordinates. So this says they're 5 by 5 pixels, and this means that they will be displayed in blue. All of the ill patients will be displayed in red instead. And the image is saved using a session key to ensure that everyone using the site will get their own images. So you won't get each other's images. And yeah, so I only have 2 patients on this map, which is not enough to do any serious analysis. So I also wrote a function that just generates random patients. So let's go over that quickly. So just loads the image. It creates 10,000 random X and Ys, and it plots those on the image, and it saves those in the database in the patient list. And yeah, that looks like this. So here's 10,000 patients that do not yet have a flu Boolean value, so they're all blue right now. And yeah, these are just uniformly distributed. So that's not how they would be distributed in practice, but it's good enough for the presentation. And I'll show you that I implemented a way to deal with non-uniformly distributed patients, so it shouldn't affect the results. So next thing we're going to do is we're going to randomly infect some patients. So what I'm doing is I'm picking 3 places on the map randomly, and then generating 3 random covariance matrices to serve as oval shapes around those places to infect patients. As you can see, there's probably more patients here and maybe here. And other than that, there's just randomly infected patients across the map. So how that's implemented is in here in infect. So all patients our patient data is loaded, and then the patients are just so the epicenters are just randomly generated with the random covariance matrices, like I said. And then patients is called for everything to do with patient manipulation, and they're randomly infected here. So let's open that file. So this is the randomly infect function. So it takes the set of patients, epicenters, and covariances of the flu epicenters, the shape of the image, and the session key to save some test images. And there, so we're using the multivariate normal, which is a SciPy library to actually make a probability distribution, and we're adding the 3 different probability distributions together. So right now I'm using 3 epicenters. This could be any amount of epicenters that's generated, but 3 looks nice. More than that would become crowded on such a small image as well, and I would have to make smaller epicenters, smaller covariance matrices for that as well. But yeah, I felt like this would be a good number for presentation purposes, but it should work with any amount of epicenters. So the probability distribution is plotted by normalizing the probability from the minimum probability to the maximum probability. Um, so that image isn't what you just saw. This is saved for the next function, and then patients are randomly infected. So yeah, these are just some numbers that turned out to work well for me. That's not a lot of other reasoning behind this. It just seemed like the distributions that this gave me. So this seemed like there would be believable flu distributions to me. So so the reason I'm generating them like this means that they're still in the areas where the flu is most prevalent. Most people still aren't infected, and in other areas there's still like plenty of people with the flu. Uh, just to show you some realistic data. And then so the next function finds the epicenters, but I'll stay on this image for now just to go over the algorithm first. So I'm using mixture Gaussian, um, and the that's basically a more advanced function of using k-means. So the k-means algorithm just says find me k-means in the data that would accurately represent the data. So what you would do is right now I'm telling it there are three epicenters. There are ways to first find the number of epicenters that would be optimal. But yeah, for now I'm just telling it that there are three of them there. And k-means works by just picking three random data points, then seeing which data points would belong to that mean, and then moving the mean to the center of those data points, and then iteratively doing that until a local optimum is reached. And yeah, that would generally give you 3 points that accurately represent the data. But since my data isn't all just round distributions, but are ovals, I'm using a mixture Gaussian, which does the same thing, but it doesn't just estimate the means, but it also tries to find the covariance matrices in the same way. So it picks three ill patients, and then it says, well, if this was a distribution, uh, then which patients would all belong to this mean, and which patients would all belong to this mean, and which patients would all belong to this mean. And then it finds the mean of that data and the covariance of that data, and it puts the mean at the found point and the covariance at the found point, and it tries to find which points belong to that data point, to that mean again. Um, but that's not entirely how I implemented this, since the large amount of noise makes mixture Gaussian very impractical here. Since data points that are this far out generated by a Gaussian that has its mean over here would cause it to have a very large covariance matrix, so very large values in the covariance matrix, just because otherwise it wouldn't be realistic that these data points would be generated by this by this mean. But in practice, these data points might not at all be generated by this mean. So I adjusted the algorithm a little bit. Instead of using the ill patients as data points, I'm calculating the flu density. So I'm taking 10 by 10 areas, and I'm calculating how many ill patients there are in that area um, as a ratio of how many patients there are in that area. So I'll show you the code for that over here. So that's an experiment that's in mixture Gaussian. And so the patients are loaded, the image is loaded, and the flu density is determined in patients.find flu density. So we'll go back here. That's down here. And all patients are just are grouped together. And then so here we actually find the density, and there's a density of 0 when there are no patients at all in a little block. And then what I'm doing is I've made a cutoff value of 8.5%, and that just turns out that it works with this distribution. So that would need to be fine-tuned if you were to use an actual data. So I'm saying if under 8.5% of each of these density points of patients have the flu, then it's not a data point. And if over 8.5% of patients in a data point have the flu, then it is a data point. So that does really well to reduce outliers in the data, and it kind of turns out it limits the the infected patients to two groups. And yeah, so we're just doing the cutoff function here, and we'll go back to the code right now. So we're finding the flu density, and we're doing a cutoff. We're doing it at 9% over here. I see. I thought I'd change that to 8.5, but maybe 9% works better. And then we're just using the mixer Gaussian function. So yeah, implemented it over here at the bottom, but that uses the sklearn library. I could have implemented this myself, but I mean, when there's already a very good implementation of it done, then there's no real reason to do it again. So the mixer Gaussian is found. I'm taking the means and the covariance matrices from that. I'm saving those, um, and the probability distribution of that is plotted again. So yeah, let's see what probability distributions we get. So let's click Find Epicenters. So this is the generated input. So I'll show you this first. So there's three means, one over there, one over there, and one over there. And the covariance matrices are over like that, over like that, and over like that. As you can see, there's like this could be interpreted as one distribution. So yeah, let's have a look at what my program finds. And yeah, as you can see, these two are basically found, and then in order to get a third one, my program thought there might be a very long, narrow distribution over there. Um, sometimes that happens, but I think it still works pretty well when two or three have been found. And then when you go to look at the data to try to analyze why that third one was found, that's probably these points over here, is what I'm guessing. But yeah, let's go back there. And so these are the distributions found. You can try it out for yourself. Try multiple times. There's random new data generated every time you click Generate Patients. So we generate some patients again, randomly infect them, and then we find the flu epicenters. So this is the input distribution, and that's the distribution found. So that looks pretty close. And then what we can do is we can say, am I at risk? And what am I at risk does is it looks at these distributions. It loads the address of the patient that logs into onPatient, and so it calculates the Mahalanobis distance. So let's have a look here. So let's find me. So yeah, it loads your location, and then it finds the address, and it basically has four replies it can make. So it can either not find your address, which in which case it says something like we couldn't find your address. You can say not on map, which means your latitude longitude is not on the map, um, or it either finds that your so it calculates the Mahalanobis distance, which is just this formula. And then if the distance is small, and then it says you live close to a flu epicenter. If the distance is large, it says you do not live close to a flu epicenter. So in this found distribution, our patient lives about here, which is pretty close to this center. So it should say you live close to a detected flu epicenter. So let's check it out. There you go. Yes, your address is close to a detected flu epicenter. And then if the distribution is the found distribution doesn't have an epicenter close, then it says your address is not close to the detected flu epicenter. So some assumptions are done in these uh, experiments. Um, for example, I'm only doing experiments with uniformly distributed patients, but taking the density of all those patients should take care of patients being distributed in a completely different fashion. Something else is I'm assuming that there are three epicenters in the data right now. But like I said, there are some algorithms to estimate what epicenters, what number of epicenters is optimal. Um, so yeah, I think that's it.